Getting two voices. Where is it from? Okay, yeah. Okay, so last class we completed VAEs, right? Hello?
Yes, sir. Yes, sir.
Okay. So for computed, okay. Okay, so maybe quickly take 5-10 minutes to look at the inference. I think training of VAE was done, I suppose. And I hope that you people could revise everything that we had done in the wake of exam, right? So that you are up to the speed. Okay, so what I will do today is like initial 5-10 minutes, I'll just complete the inference part of VAE. Okay, uh, just 10 minutes, and then we'll move on to the diffusion models. Okay, so that's what the plan for today is. So before we continue, I just want to see how many classes are we left with. 19th we have one class. 26th we have one class. Two. Second also we can have a class, right? 31st is Diwali. Yeah.
Yes.
1, 2, 3, 4. Okay. 4. And 9th, 5. And 16th also we can have a class. So even though they have said that 14th is the last working day, last class day, we can also have a class on 16th. So that there will be 1, 2, 3, 4, 1, 2, 3, 4,
5 including today.
5 including today. Yeah, I think that's good. So what I'll do, no, today we will start the DDPM diffusion models. Maybe next one more class I will complete DDPM. Okay, so that will leave us with 3 more classes. Yeah, that's good enough. So one class for autoregressive models and LLMs, and I think yeah, that's good. We can cover a lot more ground.
Sir, but
Okay,
we didn't do VQVAE
we'll
and
do that.
use.
Yeah, I will do that today. So initially today, before I complete, no, I'll do inference on VAEs and will do VQVAEs, and then we'll go to diffusion models. Okay, started then.
Sir, sir, for 2 minutes, can we just go through the passes once for the decoder encoder?
You mean the training you are saying?
Yes, yes. Just
I'll,
the
I'll,
passes.
I'll do that. I'll do that. So this is there in your second assignment, right? So when you implement it, it will become much more clearer. Anyway, so I'll do that. Okay. Okay. So as you know, right, we have these two components, the encoder and decoder. Encoder is probabilistic. Okay. I also told you why this would be a reconstruction cost, right? Yeah, we have done that. Okay. Why would the log likelihood becomes reconstruction cost? Okay, that also we have done. Good. Okay. So here is how a VAE works. So you take a sample Xi. This is of course for training. Take a sample Xi, which is the data sample, pass it through the encoder. This is the forward pass. So once you pass it through the encoder, you will get a mean and a variance. Typically, how is it done is, if K is the dimensionality of your latent space, the output of the encoder, is, this is d-dimensional. This is d-dimensional, okay? And this will be k-dimensional. So typically what will be done is, this will also be a k-dimensional vector. See, actually it should be a k-square dimensional vector. People take it as k-dimensional vector by assuming a diagonal covariance. Okay, if you assume this to be a diagonal covariance, then you only have k parameters, right? Because it's only a diagonal matrix. So input is a d-dimensional vector, which is an image or whatever, right? And the output of encoder will be 2k dimensional, where first k dimensions will be corresponding to the mean and the next k dimensions correspond to the variance. Okay. Now, once you get the mean and variance, what you do is you sample a Gaussian distribution outside of the neural network, epsilon j, and you do this reparameterization, which is you add this mean that the output of the encoder has given, okay, uh, to epsilon, which is scaled by sigma. That will give you a zj. So take that zj, okay, and pass it through the decoder, and the output of the decoder is taken to be xj cap. So this is one forward pass. Any questions on this?
No, sir.
Sir,
Okay,
when
this
we
is
say
uh,
variational inference,
hmm.
sir, like what do we mean by that?
No, hold on. I still not come to that. We are not talking about inference. We are only talking about training now. See, one forward pass through encoder and decoder is this. That much is clear. So pass a
Yes.
sample through the encoder, get your parameters, reparameterize it, sample outside the neural network, reparameterize, and then again pass it through the decoder, you get an XCAP. So that is one pass through the encoder decoder. Okay. Now to train the encoder, what you do is encoder has two losses, right? One is the KL loss. This is to train the decoder. We saw how to train the encoder here. Yeah. To train the encoder, we had once you get the XCAP, right? You compute this um, uh, reconstruction term, okay, and then you backpropagate it by keeping the decoder parameters fixed, okay. And there is also a once you come to the input of the decoder, you have the KL term also. Differentiate that KL term with respect to the encoder parameters, and then differentiate through this reparameterization term, and then backpropagate all the way through the input of the encoder. So that is one backward pass through the encoder. Is that okay? Any questions on this? So to train the encoder, you'll have to do one forward pass through the encoder and decoder, and then one backward pass through the decoder and the encoder again. While you are doing backward pass through the encoder, you also have to add the KL loss. And for the decoder training, one forward pass through the encoder decoder, get the output of the decoder, compute the reconstruction loss, and one backward pass through the output of the decoder. That completes training VAE. Any questions on this? Okay. So once this is trained, what do we do with it? Is it not?
You can just write anything, sir, then it will score.
Oh. Inference with VAE. Okay, so post training, VAE can be used for two tasks. Okay. The first task is posterior inference. So as I said in the previous class, what do you mean by posterior inferences? Given a data point X, okay, so let's call that as like test or something because this is not in the training data. Okay. Find the corresponding latent vector, also called as embedding. this is what is called as, that is the test. Okay, so this is what is called as posterior inference. I told you, right? Any latent variable model, one of the advantages is that once you train a latent variable model, you can get an embedding corresponding to the given data point. That is what we do in all these encoder decoder based LLMs also, right? The encoder will give you an embedding corresponding to data. Now, how do you do that? Take the encoder, which is trained, okay? Star. So you pass X test to this, and what you get here is get mu phi star at X test. You get sigma phi star at X test. Right? This is what you get, right? Now, the embedding of X star X test, there are multiple options, right? Can be taken to be mu phi star itself. So this itself can be taken as an embedding corresponding to X test. This is one possibility. The other possibility is to sample an epsilon from normal 0, 1. Okay. Let's call this embedding 1. Normal 0, 1. And then take Z test to be equal to, let's call this epsilon t. Epsilon t times, basically you do the reparameterization test plus mu v star X test. This now becomes embedding for X test, can be Z test also. This, let's call this embedding 2. So you can get, so for any data point, right, you can get an embedding this way. Just pass it through the encoder. You either take the mean of the encoder itself as the embedding, or you do a sampling outside of the neural network, reparameterize and take that as an embedding. So now how do you use this embedding is up to you. You can use it for a class, you can use it in a classifier. See, what happens is, we know that the dimensionality of the test that this is much less than dimensionality of X test. So what can be done is, you can train a classifier using Z test, right? Or you can do arithmetic in the embedding space and all that, right? So I can say this Bangalore weather since last 15 days has made everybody sick. So Z test can be used for classification. Okay, or like compression. You can do contrastive learning on top of it, etc. We'll talk about this contrastive learning later in the class, later in the course. So basically, you can use this embedding to whatever uh, effect that you want. Okay, that's the idea. So this is called posterior inference. Any latent variable model, right? You can get this, meaning post training, you can use the encoder to get the embedding corresponding to unseen data points. I mean, of course, you can get embeddings corresponding to the training data as well. Entire data, you can get the embedding. Take the trained encoder, pass the data through the trained encoder, and you get the embedding and use it for whatever downstream task that you would need. So that is about posterior inference using latent variable models. Any questions on this? Yeah, Shirisha.
Yes, sir. Sir, so when you said Z test can be used for classification, what kind of classification you mean? Not
Let's say
clear.
that you have built a VAE on MNIST, right? Now you want to train a classifier on MNIST. So typically what you do is you take the images and train a classifier on MNIST, right? So instead of doing that, you take the embeddings on the MNIST and you train a classifier using embeddings. Does it make sense?
Okay, so basically we are trying to classify the class of the image, is it?
Anything. So it doesn't matter, right? Your input can be image or it can be text or anything, depending upon what sort of data you have. But the idea is that you can, instead of using X test, you can use Z. So a more interesting question is, what advantage do you get by using Z instead of X, right? Now, the answer to that is, at least if you have learned a good encoder decoder model, right? The hope is that the embeddings that you have gotten is well clustered, well behaved. Because as I told you in one of the earlier classes, these naturally occurring data will be in very high dimensional spaces and they will all be scattered, no, because of curse of dimensionality. They will not be well clustered. If you learn a representation in a lower dimensional space, it will be much more clustered and classifiers would behave much better in the embedding space compared to the data spaces. The hope. Tell me this, in your assignment, have I asked you to use these embeddings and build a classifier?
Yes, sir.
This is exactly what I've asked you to do, right? Train a VAE and then get the corresponding Z's and then use it in a classifier. And I think I've asked you also to compare this with a classifier that is built only on the data space also, right?
So
Yes, sir.
that
Have I? Let me just open the assignment and see.
Yes, I've asked a CNN based
I have
classifier.
asked you, right? Yeah. So that's what it is. So first you have to use a CNN and classify the data, and then use these embeddings and reduce the network size and simply use an MLP and see what happens on top of it. Okay. Yeah, Sarvesh.
So for this reparameterization, so
Hmm.
this is the sigma should be raised to half, right? Because we need some standard deviation type component to be added, right? So
See,
this is
that depends on what you are representing as sigma. No, I am representing that root of that itself as sigma. Depends. That's just a scaling factor, right?
so we're directly getting standard deviation type thing for of the
That is
encoder.
what I'm saying, right? So now if you represent the output of your encoder as standard deviation, then you raise it to power of half. If I say that it's the variance, then you don't have to. Depends upon how do you see it, that's all.
Okay.
Yeah. Okay, Sanjit?
Sir, is this the right time to ask that about variational inference? Like,
See, this is posterior inference, okay? Posterior because what you are actually calculating here is you are calculating P theta, P phi star of Z given X, right?
yes,
Technically speaking, not P. It's I was going to say that this is,
Q,
yeah,
Q
this
P
is,
star.
yeah, Q phi star of Z given X, correct? Right? Now, this is inference, definitely, because given an X, you are giving a Z, okay? And this is posterior. Technically speaking, you can actually call this variational posterior inference. Variational posterior inference. Variational because we don't have access to P theta star z given x. This is the true posterior distribution, right? We are using a variational distribution. Variational distribution, which is Q phi of z given x, to approximate it. So that is why it's called the variational posterior. Okay. In fact, in your exam, I had asked you to start from the KL divergence between these two distributions and derive the elbow. Correct? Do you remember that question?
Yes, yes, sir.
See, I had told you that you start from the KL divergence between the variational distribution and this, right? And show that minimizing this will boil down to the elbow objective that you optimize in VAE, correct?
Yes, sir.
So this is exactly what it is, right? I mean, you can actually see the entire analysis that we did in VAE was by saying that we want to maximize the log of the data likelihood under the latent variable model, right? That's how we derived the elbow. The entire story can be constructed via this route. Okay, it's only an algebra. You should just write this scale divergence and write this posterior in terms of the joint distribution between x and z and marginal, and then you get it. In fact, it's pretty easy. I hope that uh, like a lot of you could get this, crack this. Did you do that? So you just have to write down the
Yes, sir.
definition of KL divergence and use Bayes law and show it. It's not at all difficult. Okay. Now, yeah. So basically, the reason I asked you that question is to make you appreciate this, that it is called a variational model because while we want the true posterior distribution of z given x, because we do not have it, we approximate that using another distribution, which we call the variational distribution, which represented by q phi of z given x. So the objective is to make sure that the posterior of the true, posterior under the true model is going close to the variational posterior, and you minimize the KL divergence between them. That is the objective. Okay. So now that's why you call this, I mean, when you estimate Q phi of z given x under a trained model, you call that as variational posterior inference. Posterior because you are getting z given x. This is because posterior. Inference because you do it under phi star post training. Is this all right, Sanchit? That's why it's called variational posterior inference.
Okay, sir.
Okay, so this is, I mean, we were talking about inference with VAE, right? One is to get the um, embeddings. The other thing that you can do with this is obviously data generation or sampling, because it's a generative model. To do data generation or sampling, how do you do that? Is that take the decoder. See, this is exactly what happens in a language model also. Okay, encoder decoder based LLMs, exactly the same thing happens. The encoder is used for inference, okay, and the decoder is used for generation. Same thing with all encoder decoder models. Now you sample Z from normal 01 and give it to the trained decoder, which will take Z and give you an X. Okay, it will give you X cap. So this is the generated data point. Now, see, a true decoder, I mean, while training, decoder is trying to take samples from Q phi of z given x, isn't it? You get what I'm saying? See, decoder is trying to see samples from Q phi of z given x and give you sample from p theta of x given c, right? But now you are sampling from normal 0, 1, not from Q phi of z given x. Why would decoder help you? Do you see the question?
Because we are reducing the KL divergence between P theta of z.
Exactly, right? Exactly. So now what happens is, now post training, Q phi of z given x, okay, would reduce to normal 0, 1 because of the KL term in elbow. Therefore, z coming from Q phi of z given x is equivalent to C coming from normal 0, 1. In fact, I've asked you to do this also in your assignment. Okay. That once you train the decoder, you sample Z from normal 0, 1 and then give it to the decoder. You get the generated data. Now, in an LLM, right, we will see that later. We will do what is called as conditional generation. Because all these GPT, etc., what they do is they take an input and then gives you an output, right? It's not unconditional generation, unlike in a VAE. I mean, you can also tweak the VAE to do conditional generation. All you have to do is, as I said, we looked at conditional GAN, right? Similarly, you can do a conditional VAE just by appending another conditioning variable in terms of text embedding or one hot vectors, right? So, but basically the idea is that once you train, you take the trained decoder and then you can do sampling or data generation. So now encoder becomes the inference model and decoder for data generation. See, the idea is if you take, let's say, a naive autoencoder, okay, that has an encoder and a decoder, X and X cap, okay. Now, what happens is, let's say that it will give you Z, and you simply have a reconstruction task here. Excuse me. So you have a reconstruction task here. Now, this, if you train a naive autoencoder like this, okay. Now, post training, you can only use this autoencoder to do inference because you can take the encoder and given an X, it will give you a Z. But you can't do generation using this thing because the distribution of the latent space is unknown. In a naive autoencoder. Okay. Now, what do we do in a variational autoencoder is if you see that, we will say that, look, I don't only want I not only want my decoder to reconstruct the data, but I also want the distribution of the output of the encoder, okay, to follow some distribution of interest so that once I train this, I can sample from a known distribution and then use the decoder as a generative model. Right? So now VAE, you can see VAE as an autoencoder with a regularization on the latent space. Okay, such that the distribution of the latent space should follow a Gaussian. Or a predefined distribution, let's say. In general case, it will be predefined. Gaussian distribution. Is this all right? So in an autoencoder, what will happen is there's an encoder and a decoder. You would say that, okay, the data has to get encoded into some latent space, and from the latent space, you'll have to get back to the data space, right? In a variational autoencoder, we'll say that, okay, we just do not want the data to be reconstructed. We also want the latent space to follow a particular distribution of interest. Okay, so that why do we do this is because post training we can sample from this distribution of interest and give it to the decoder and use it as a generative model. Is this all right? So that way, right, VAE can be seen as a regularized autoencoder, an autoencoder with a regularization on the latent space such that the latent space follow a particular distribution of interest. Okay. Yeah, Sanchit?
Sir, but the normal distribution, that is a very wide space, right? So it's not possible that for every sample within this normal distribution, we will get a proper image that is similar to the original data set. So like that's where like we try to learn on the poles or the clusters.
See, uh, why you can see this as a reconstruction plus a regularization, you should always remember how did we get to this objective. We got to this objective by minimizing the KL divergence between the model distribution and the true data distribution, correct?
Model distribution and true distribution. Correct.
See, how we started, how did we get this? This was our elbow, right? Whatever I've written here is our elbow. That is why I don't write the loss function of VAE as simply reconstruction plus KL, simply because I want you to appreciate where did this come from. This actually came from the elbow, right? Now, what was that? That was the KL distribution, KL divergence between Px and P theta. That's what we started from. Now, doing all this, we are actually reducing the KL divergence between Px and P theta. So now, if we have done it right, then no matter what this distribution is, it can be normal or anything, the VAE has to sample from Px because we have technically reduced the KL divergence between Px and P theta. Does that make sense?
Okay.
Because the entire model has reduced the KL divergence between Px and P theta. If you have done it right, then this objective should lead you to sample data points from Px.
Okay.
Ravindra?
Yes, so in the assignment, what we observe is the reconstruction loss is, decreasing pretty fast, but we see that the KL divergence, it's hard to reduce. It keeps
Correct.
generally
Correct.
increasing. So what's
correct? Correct. That happens. See, that is because something which is called a posterior collapse. So I'll talk about it. Okay, so I'll come to that. So this is how what do you do in a knife VAE, right? There are lots of improvisations that people have done over a knife VAE. I'll not talk about all of them. I'll only talk about like one of them, which is the vector quantized VAE, which is sort of state of the art VAEs that people use. Okay. Yeah, that is precisely because the observation that you have made in your assignment. Okay. So there is something called posterior collapse in VAE. I'll talk about it. Collapse in a knife VAE. sort of related to the question that Sanjit asked. We'll tell you what happens is, see, in the naive VAE, what's happening is, so recall that in a VAE, now Q phi of z given x, okay, is forced to go to normal 0, 1, okay, irrespective of, okay, for all x, isn't it? See, now Q phi of z given particular x, this is what it means, no? X, by conditioning it on x, this means x is equal to a particular xi, okay? Now for all xi, we want this to be equal to normal 0, 1 in a VAE, because we are reducing the Keil divergence between these two, correct? You understand? Now, okay, so is this clear to all of you that in a VAE, this Q phi of z given encoder distribution is forced to go to normal 0, 1 for all x? Okay. Now, what is the consequence of it? The consequence of this is that, okay, do you people know of this idea called bias variance decomposition, bias variance trade-off?
No, sir.
Okay. See, whenever you regularize a model, okay, so if you take a learning model and you regularize the model, what will happen is, I mean, you might be knowing it in a different name, perhaps, right? See, if you over regularize a model, what will happen is, why do you regularize a model? You'll regularize a model because you want to avoid overfitting, right? Now, if you over regularize it, the model will go to the regime of underfitting. Now, if you do not regularize it, then the model will go to the regime of overfitting. Right? It is this trade-off between the underfitting and overfitting is what is called as the bias variance decomposition. So that is a topic by itself. That's exactly what happens here. Okay, so I'll tell you the consequence of this is the following. If Q phi of z given x, okay, approaches normal 0, 1 for all x, okay. Think about it. Suppose your Q phi of z given x approaches normal 0, 1 for all x. What is the consequence of it? Then the decoder will have a difficulty, in reconstructing. Why do you think so? See, you see what is happening. Let's say that there are two x, okay, x1 and x2, okay. Now, Q phi of z given x1, okay, is equal to Q phi of z given x2, and both of them are, let's say, normal 0, 1. Right? Suppose this happens. If this happens, then if you get a z1 from Q phi of z given x1, okay, and z2 from Q phi of z given x2, right? So decoder will not be able to differentiate between z1 and z2 because both of them are coming from the same distribution. You see this? This is what is called as posterior collapse, right? which means that for all x, okay, q phi of z given x is collapsing to a particular distribution by design. This is a consequence of elbow, right? We are not like we can't help. This is what is happening. So now, since x1 and x2, rather, since for all x, q phi of z given x is going close to one particular distribution, right? Decoder will have difficulty in trying to reconstruct, uh, or rather, see if it can differentiate between each sample input sample, it can reconstruct easily, isn't it? If it cannot differentiate between the latents corresponding to two different samples, then it will have hard time reconstructing it. Do you see this point? Does all of you see this point? Any questions on this? Yes, Nirmat?
So this happens only in naive VAE or
Correct. It happens
only
only in
naive?
VAE. Yeah. We'll see how to circumvent this problem. How do you solve this problem? Actually, you should have seen this in your assignments if you have started implementing it, right?
Yes, sir.
Yeah. So I'll tell you what happens. This is not what happens. See, in the kind of architectures that we use, right? Reconstruction will not suffer. The other way happens. This is only half of the story. I'll tell you the other half. Maybe I can ask you I can take questions after this. This is posterior collapse. Okay. Now, uh, suppose okay. So I suppose the weight on the KL term is reduced. Now, what do I mean by that? Oh, the loss function in VAE looks like this, right? You have the reconstruction plus the KL term. Call this normal 0 only. Okay. Now, this is how it is. I mean, in the naive implementation, both of these terms are equally weighted, right? So there is another version of VAE called a beta VAE, okay, which is simply adding this beta term to the KL where your beta is between 0 and 1. Okay. Now, so higher beta, right, corresponds to more weight to KL. So this is beta VAE, improvisation on VAE called beta VAE. Higher beta corresponds to more weight to KL and vice versa, right? So now let's say that, let's come to this. Suppose I give more weight to KL, what will happen? This may lead to posterior collapse. We already saw that. Okay. Now, if you have, suppose I give very low weight to beta, what will happen? This means that more weight to reconstruction, more emphasis on reconstruction. This means that the reconstruction happens very nicely, okay, because now the decoder can, I mean, see, this implies, okay, lower beta implies q p of z given x, okay, may not be equal to normal 0, 1 for all x, okay. So this implies that reconstruction is easier. reconstruction is easier because why is this? Z1 and Z2, okay, can be different for X1 and X2. See, if you have two different latent codes for different input samples, then it will be easier for the decoder to use that latent information and then reconstruct it back, right? You see what I'm saying? Now, okay, reconstruction is better if you reduce the weight on the KL divergence, but it should come with a cost. What is the cost? Can somebody think about it?
So there will be inference collapse.
Meaning the generation will suffer. However,
Yes.
the generation quality will suffer. With lesser beta. Why is this? This is because, see, remember that what we do, what we do post training is that we take p theta star, okay, we sample from normal 0, 1. Okay, now if q phi of z given x, okay, is not normal 0, 1 for all x, then during generation, okay, sampling a z from normal 0, 1 and passing through the decoder okay, may not lead to data samples. Because, why is this? Because decoder has seen q phi of z given x during training, okay, which is not equal to normal 0. That's why. Understood? Now, for the decoder to work, you need q phi of z given x to be normal 0, 1 for all x. Okay. And if you make that, then what happens is the reconstruction quality suffers while the generation becomes okay. So now there is a trade-off between these two. In fact, if you look at the beta VAE paper, they will show you that with different values of beta, you will see the trade-off between reconstruction and generative quality. What I suggest you is to implement this beta VAE in your assignments. When it comes with no cost in the sense that you just have to have a weight factor on your KL divergence term, and you experiment with different betas, and you would see that if you have a large beta, then the reconstruction will become difficult. Okay, why the generation will be okay, and if you reduce the beta, reconstructions will be better, will the generation quality suffers. In fact, you might have seen, right? I mean, if people who have read the architecture on VAE, people you might have seen people saying that VAEs results in blurry generation, right? Blurry images. So that, what is that? That is simply saying that if your q phi of z given x is not normal 0, 1 for all x, what will happen is if there is a deviation between what the decoder has seen during training and what it sees during inference, then the images that you generate will not match that of p theta, and that's why quote unquote blurriness comes into generation quality. Now, to avoid that, if you make your reconstruction very strong, okay, by reducing the beta, then the generation quality suffers, and there is this trade-off between these two. Okay. Okay, so now we will take questions. Yeah, Vivek.
So will making beta 0 convert this into an autoencoder?
Exactly. That's a good observation. Yeah, if you make beta 0, then it will simply become a naive autoencoder. Lesser and lesser beta will always take it closer and closer to a naive autoencoder. Yeah, Ms. Shirisha?
Can you hide this side panel?
Can you hide the side panel? How do I do that? This one? No.
Yeah.
It opened
Full
up
screen.
something else.
So full screen is there on the
top
top
right.
right.
This is. Why is this not moving?
Write something, it will start moving.
Not recognizing at all. What happened to this? Something happened. I mean, I'm not able to see this. Can somebody tell me what happened with this?
Sometimes
Maybe
it gets stuck, sir. Yeah.
Oh,
post skill
We
and
can
then
just
start.
close and open again.
the age-old solution, huh? Restart.
Solution to all problems.
Huh?
I said solution to all problems.
Yeah. Oh, yeah. It actually worked. Okay. Let's take questions. Vivek, do you still have questions or is it done?
Sir, yes, I have a question. Suppose we
Hey,
change.
yeah, hold on. Just one other side thing. See, I have been calling all of you by your first name. I hope you don't mind. I mean, for all we know, all of us are of pretty much same age, or you might be like seniors to me. So please don't mind. And also feel free to call me Pratosh. I don't mind. So you don't have to call me sir. That's too British. Just take my
That's
name,
okay,
right?
sir.
So yeah. I mean, I
It's
mean
okay,
it. I
sir.
really mean it. You can feel free to call me Pratosh, and I'll be happy. And also, right? I mean, don't feel irked because I call your first names out. Okay. Because if I start calling you sir, so there's so many 85 people, right? Sir and madam. So you don't know who is who. That's why that's why the names are given anyway. So anyway, go on, please.
Yes, sir. So one question is, suppose we have a generation for a given Z, and I change Z a little bit. So will the output look just a little bit modified, or
Yeah. That is how it should happen, right? I mean, that is how it should ideally happen. If you have
okay?
trained it well with good architecture, that is how it will happen. See, that is why in GANs, right? I think, did I include this in your assignment? Did I ask you to sample two Z's and then do
Yeah,
interpolation between them?
interpolation.
Yeah.
Yes.
So did you see it changing smoothly?
Yes, sir. Yeah.
Yeah,
We
that
saw that.
happens. Yeah, it happens if your latent space or the embeddings that you have learned are good. In fact, when we come to some of these language models, right, you would see that in this thing, right? What was that thing? Was it bird? It was not. Which was that, right? I mean, that famous example where they show that man minus king embedding corresponding
Yeah,
to
word to vec.
word to vec.
Word
Yeah.
to vec.
So word to vec, right? That should happen. So it should semantically make sense if you have learned good embeddings,
Okay.
right? So it depends. See, that is why imposing this sort of a constraint, or rather a distribution on your latent space, makes sense.
Okay.
Yeah.
Sir, and one more question, but yeah, I think it's not maybe the right time to ask. But if we have a picture from somewhere else, and if we want to find its Z, how can we do that?
I told you, right? That's what you do. That's what the inference is. You take a pre-trained encoder or a VAE, pass it through the encoder. In fact, we will see that. See, you know the stable diffusion, right? All these the state-of-the-art diffusion models, the Imagine or whatever, the Googles and all these, they don't do diffusion models on the on the image space. They do it on the latent space of a VAE. In fact, a VQ VAE. Once I talk about VQ VAE, I'll tell you that. So basically, take the trained encoder, pass your data through the encoder, get the embedding, and then use it. This posterior inference. That's exactly what you see on your screen. You train your VAE on, let's say, ImageNet, and keep that, right? And given some new data, pass your data through the encoder, get the embedding, and use it for whatever reason, whatever downstream thing that you would want to do.
Yes, thank you.
Okay. Sanjit?
Sir, in this in this description for posterior collapse, so sir, it is high since the normal distribution is a very large space, and we have a finite set of images, like input images. So, isn't it possible that we get each Z that is unique for a given X?
Yeah. If you recall, our encoder is probabilistic. We are not asking the encoder to give the Z. We are asking it to give the mean and variance.
Okay. Okay.
That's precisely why we make it probabilistic. It's not the Z that you get the parameters of the distribution. And by construction, you are asking the output of this encoder or the mean of this encoder to go to 0 for all X. Even though the distribution, the support of the distribution is broad, what you are predicting is the mean and variance, not the Z itself.
Okay. And sir, one more question. So I was a bit confused with the term variational Bayesian. So is it same as the variational inference we talked about?
Yeah. It's Bayes because, see, autoencoding variational Bayes is what they call the VAE people. It's Bayes because, again, this, if you had done this exercise that I had given you in exam, this one, you use Bayes theorem to get this elbow, isn't it?
Correct.
Yeah, that's why it's called variational Bayes. Okay, variational because you use a distribution, a variational approximation to p theta of z given x, which is unknown. Yeah. Okay. Indrajit?
Yeah. What is the difference between reconstruction and generation?
Reconstruction and generation. Okay. See, reconstruction is that you take an x, pass it through the encoder, and take that z, okay, that the encoder gives you. When I say z, it is this reparameterized z, and pass it through the decoder, right? And you expect the output of the decoder to be exactly the same as that of the input. That is reconstruction. Correct? It's the first term.
Yeah,
generation is see, even after training, you can take a data point that is there that you use for your training, pass it through the encoder, get its Z, and pass it through the decoder and expect the decoder to give you the exact same X, isn't it? See, post-training, nobody is stopping you from using the training data and passing through the encoder and giving it to the decoder, isn't it?
Right.
Yeah, so that is a reconstruction thing, isn't it?
Okay.
So generation is that you take a Z and pass it through the decoder, you get a new point that is not there in your training data. That's sampling, of course. But you can do reconstruction on training data as well. How do you do it? Take the X, okay, and pass it through the training, the encoder, get the Z, take that Z, pass it through the decoder, and you expect the same X to come back.
Okay.
Yeah?
Thanks.
Okay. Raghavendra, still have questions?
Yes, sir. In the parameterized model for decoder, we are only considering the mu, and we are saying that the sigma is identity.
Correct.
Can we also take sigma? I mean, and what implications that will have?
Yeah, you can, and then you have to, again, to generate, you have to do another sampling, right, at the output of the decoder as well, right? Typically, sigma is not taken, but yeah, there's nothing that stops you from doing it that way. Typically, it is not done.
Okay.
Okay. Harish?
So depending on our use case, that is whether we are doing reconstruction or the generation, so we can change the training objective to have this KL divergence regularization term or not. Right?
Correct. That's a good point. Yes, that is why it's like a knob. Beta VAE. This beta is a knob. Depending upon what do you want, right? In your what you are training your VAE for, you can tweak it the way you want. That's a good point. Yes.
So we can have two different models for two different tasks.
Yes. Okay. So in fact, in your assignment, I encourage you to actually do that. Sweep over beta and see the effect of what happens on your VAE. Yeah. Srinath?
Yeah, sir, my doubt is about this posterior collapse. So here, due to the tail divergence, we expect the mu and sigma outputted by the encoder to be close to 0 or 1, but not
for all x. For all x, correct.
For all x, but it should be exactly 0 or 1.
I mean, yeah, if the training has happened properly, yeah.
Right. And so is this somewhat of an adversary nature? Because if the KL divergence becomes 0, then the reconstruction loss will explode. And if
No, it should not. It should no, right? Why should it explode? See, as I think one of Sanchit was saying that, I mean, you are asking it to make it Gaussian distribution, zero mean unit variance for all x. But even within zero mean unit variance, you have infinite support. No, you can place your z different places. But practically what happens is because you have like limited capacity encoder decoder, right? All these Z's would be placed on very close to each other and uh, discerning the difference between those two will become difficult to the decoder. There's no adversary here. See, ideally, if you have infinite capacity encoder and decoder, both the objectives can be achieved, isn't it?
Because the encoder is technically not, as you said, right? It's not giving Z, it is giving the parameters
Doesn't matter. Let's say that it will do perfectly and it will go to zero mean and unit variance for all x. And suppose your decoder has infinite capacity, right? As long as for two x's exactly the same Z is not getting generated from the sampling, the decoder can do it. And also remember that the sample that the decoder sees as input, okay, is a sample that you get outside of the encoding. Right? And also you do an averaging over it, no? See, you don't take one sample of Z and give it to the decoder. You take multiple samples of Z and give it to the decoder. So that way, if you have infinite capacity of encoder and decoder, ideally a VAE should do perfectly well. But since we have like finite capacity architectures, right? If you make your encoder to have same distribution for all x, decoder will have. In fact, that is one other experiment that you can see that keep everything constant, including the beta, but only increase the architectural size of encoder and decoder, and you will see better performance.
Okay.
Yeah. Yeah, these are very good questions, by the way. In fact, I received one comment from one of you. I mean, I don't want to know who it is, but because that's the whole point of it being anonymous. It said that you see you have spent so much time on quote unquote basics, right? Now we only have these many classes, and you're not covering the syllabus, and this happens with all courses in ISC, etc., and all that. It was sort of not so positive sentiment. But see, the thing is, a good course, right? In our opinion, I mean, good that the person said that this happens across the board in ISC. See, what we feel as faculty in ISC is that we want to prepare you to to read some of these literature independently. So the idea is not to cover a lot of breadth, a lot of papers, a lot of ideas at a superficial level. The idea is to go sufficiently deep and make you independent so that you pick up any paper in the literature and then you can read it. So even if we don't quote unquote cover the syllabus, I don't know what syllabus is, because none of the ISC courses will have any syllabus per se, especially these advanced courses. The idea is to make you think and and enable you with a lot of tools and arsenals of tools, such that you can start reading and appreciating and understanding things. Okay. So I mean, what I was coming with this, I was reminded of that particular comment, because all the questions that you are asking are very, very relevant. And then I hope, when I suspect that you're able to ask some of these questions and appreciate these things in deep, because we spend so much time on basics. What are these divergence metrics? How do you carve bounds on things, and how do you build models, etc. I think that is what is valuable, isn't it? I think we can have this discussion maybe when we have that hybrid class, when you people meet me, okay? And I wanted to have that discussion as well, right? I mean, we have to plan for that uh, post Diwali. So now that I'm talking about it, maybe we should post some dates. So second, how about yeah? Can we do it on 16th itself? The last class that we do. Shall we do it hybrid? Can you people plan a visit to ISC on 16th of November? Let's do it that way. So tentatively, let's keep it on 16th. Okay. Again, we will do the exact same thing. I will do it a Teams call, and I will write it on my iPad and project on screens. But whoever wants to come to ISC, right, you are welcome. I'll arrange for a physical class, and we will do it offline, hybrid on 16th. Okay. So yeah, I think 16th is the only date, because 19th, 26th we can do, but 26th is too short of a notice. But second is that Diwali week. I think a lot of you will be traveling. Yeah. 9th, I don't know if you people come back. On 9th, I have some other commitment that I can't travel to ISC. I think 16th is the only day. Let's keep it on 16th. So tentatively 16th will be a hybrid class. Okay. Plans for it. Okay. If you want to come, I mean, there's absolutely no compulsion or anything. Only if you want to uh, come and have a look at the campus and like meet me in person, you are welcome to come there. Okay. Right. So this is about posterior collapse, and this the trade-off between the reconstruction and generation. Now, as I said, people have addressed this problem in multiple ways, and there have been a lot of efforts in improvising VAE models. So one of them is, of course, this beta VAE, right, where you have an explicit scale term on the KL divergence to control between the reconstruction and KL divergence. This is one thing. The other thing, other class of methods, okay, uh, are where question is, why should be the latent prior hear some music that some guy on the streets, right? So yeah, not me. Why should be the latent prior p theta of z? Okay, be the latent prior p theta of b fixed to be normal 0, 1. See, all the while, if you notice, in elbow, the KL divergence was between q phi of z given x and p theta of z, right? Now, what did we do in a naive VAE? P theta of z is fixed at normal 0, 1, right? Which cause problems, right? Which cause the issue of posterior collapse. So a lot of people question this assumption that why should we fix P theta of Z? Now, in fact, like my first PhD student from IIT Delhi actually worked on this. So his entire thesis was on optimal P theta of Z. So now the question that can be asked is, or rather, not question because I've posted question already, call it as solution, is to learn the latent prior. Learn the latent prior P theta of Z along with the model. Along with the encoder decoder. So this is one of the key ideas. As I said, no, my first PhD student, his entire work was on this. So learning the latent prior for encoder decoder models. Why should you fix it? You will learn the latent prior itself. So what could be the best distribution that you have to impose on the latent space so that you get the optimality? Lot of work has been around this. So one notable thing is what is called as VAE, which a variational, it's called vamp prior. Okay, variational maximum a posteriori prior. Okay, this is one thing where the idea is roughly to make P theta of Z, okay, a GMM, a Gaussian mixture model, and learn it during training. This is what they do. Okay, they make P theta of Z a Gaussian mixture model, which is a more flexible distribution than a univariate Gaussian, and learn it during training. Learn the parameters of the latent prior also, right? So what will happen is the elbow will have three parameters, right? So we had theta, phi, and theta and phi, right? So there in all these methods, you will have another parameter lambda, okay, where P lambda of Z is the learnable latent prior. So the optimization will be you find theta star, you find phi star, and you also find lambda star as the minimization. You do a minimization over theta, do a minimization over phi, do a minimization over lambda, and you have this elbow. So now this elbow will be a parameter of the encoder, which is parameterized by phi, decoder parameterized by theta, and you have the prior, which is parameterized by lambda. So this is how it looks. Okay, so notwithstanding the details of vamp prior, because that's not the state of the art, right? What people observed is that if you make P theta of Z a continuous distribution and make it a GMM, right? It's again in problems like posterior collapse. I mean, while it gives you some respite, that's not the best thing that you can do. You can do better than that, which is the vector quantized VAE, which we will see. But the basic idea is that along with learning the encoding decoding, you also learn the parameters of the prior distribution on the latent space. Is this idea clear? Yeah, Raghavendra, we'll see one instantiation of this. Just a second. We'll see one instantiation of this, which is actually, as I said, no, the state of the art VAE, which is the vector quantized VAE. Even there, the idea is to learn the latent space, distribution of the latent space along with encoder decoder, called the vector quantized VAE. Yeah, go on, Raghavendra.
Yeah, so I mean, what uh, this lambda distribution, right? What it would try to come close to? Is it p theta of z given x or?
Exactly. So theoretically, what can be shown is the ideal prior, right? It's actually the ideal prior is can be shown to be equal to what is called as the aggregated posterior, which is the integral of this can be shown. The ideal prior that one would need to get the optimal elbow is what is called as, this is called the aggregated posterior. This can be shown. This is shown in the VAM prior paper.
Okay.
Yeah. So what is this? You take all the encoding distribution. Sorry. Take the encoding distribution, marginalize it with respect to the data distribution. Okay. And that is what the ideal prior has to be. That is what is shown. Okay. Again, you don't have to worry about it here. Okay, so we will see one instantiation of this idea, which is, as I said, no state of the art VAE, which is called the vector quantized VAE. Yeah, go on, Sanchit. Vector quantized VAE here.
Sir, but where we are learning the distribution on X, like it is the in maximum likelihood estimate format, right? Px given Z. So how will we be able to calculate Px then?
So we can't. See, that's only a theoretical result. See, whatever I wrote is only theoretical in the sense that the ideal prior on the latent space is the aggregated posterior is a theoretical result. That is what you try to approximate using GMM. Okay.
Okay.
It's discrete and it is vector quantized. In VQVAE, in fact, the VQVAE paper, right? The title of the paper is not vector quantized VAE. They call it neural discrete representation learning. That is the title of the VQVAE paper. Neural discrete representation learning. Okay, that's what the paper is. So basically what they do is the following. The motivation comes from the fact that they say that, you see, all the naturally occurring data, right, can be compactly represented using some discrete amount of codes is what they say. Here is what they mean by that. Okay. So let's say that you want to represent speech signals using some latent space. Now, human speech can be represented using a finite set of phonemes. Okay. So what do you mean by phonemes? Let's say that I say A and you people say A. Now, if you plot that speech signal of A, of what I say and what you say, all of them look very differently. Okay, even the different instantiations of the same sound that one speaker say will look differently, right? In spite of that, no matter who says that sound, we perceive one particular idea called a, right, or a. That's a phoneme. So phoneme is an abstract idea that you perceive when you hear speech. Okay. Now in English language, there are only a few finite set of phonemes that would represent the entire language. Okay. So that is, let's say, they have identified some 50 odd phonemes. And in Indian languages also, you have about 50, 60, around 60 phonemes. Okay. So now to represent language, all you need are 60 codes, right, which correspond to each of the phonemes. The same thing can be said in term for images also, right? I mean, if you want to represent an image, any scene can be represented by saying things like, okay, there are how many regular regular figures like rectangle or circles are present here, and like how many slant lines are here, etc. So basically, you can have a finite number of discrete descriptors, which are latent codes, that can be used to represent any kind of naturally occurring data. So that is the motivation. Okay, so that's why they use a discrete latent space in a VQVAE. They vector quantized and learnable. I mean, we know why we should learn the latent space also, right? So it is learnable during training. So if you incorporate all these ideas in a VAE, right, you will get what is called as a vector quantized VAE. We will see what it is. Is the motivation sort of clear? Okay, let me write down uh, the architecture and also the way it is done, and then we can discuss. So they make the encoder deterministic, not probabilistic. So it takes xi, okay, it will give zi. Okay, so they call it ze of xi. E corresponds to encoding. You get zei. Okay, then suppose there exists.
Sir, your screen is not moving for me at least.
Yes, it's not visible while you're whatever you're writing. Lag is there, I guess.
Is that so?
Oh, it's refreshed, I suppose.
Let's see. Sometimes network gives some issues. Suppose there are m latent vectors of k dimension each. Call them z1, z2, z3 up to zm. All zi is in R k dimension. So now these form, right, a dictionary. Let's call this. This is a latent dictionary. The latent dictionary. Okay. So what is done in VQVAE is that you find the quantized version of the xi to be zk. Let me call this z j star. Okay, where j star is the one that is the closest between z e of xi and z j. You have j to be equal to 1 to m. Does it make sense? See, what we are doing is the following. Okay, it's a 2 norm. Now, xi is an image or some data point that goes as an input to the encoder, and it will give you some vector ze. Now, what I will do is I will search for that zm, okay, that zj, which is closest to this output of this encoder. Okay, and replace that ze with that particular vector in the dictionary. Do you see what is happening? And that goes as an input to the decoder. So the quantized version of the input goes as the input to the decoder. Is this clear what is happening to all of you? Questions on this? So this is vector quantization. So this operation, right? This operation is what is called as vector quantization. Quickly, Nirmit.
So this latent dictionary is fixed, right? We have to
No,
create
no,
this
no,
site.
no, 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 no. Learnable. We'll see how to learn that. Yeah, this is exactly what we learn. I mean, I told you that the latent space is also learnable, no?
Yes.
So we will learn this.
Okay.
Yeah, Raghavendra.
So going back to the motivation, right? So you mentioned that we want to discretize it here. But if you see even in the VAEs, right, the number of Z that we fix, can't we? I mean, look at it like some
there is
basis.
no discrete. No, there is no discrete. No, it has a distribution. They don't have a fixed amount of Z.
Okay,
Z is not
these
fixed.
these are very much fixed in the sense if you are choosing
they're fixed
K dimensions, then we know exactly what they are.
No.
And nothing beyond them.
It's not about dimensionality. It is about M. M latent vectors are fixed. M is a hyperparameter. You fix the number of vectors in your latent dictionary.
Okay, and once we have learnt them, we use them as the dictionary too.
Correct.
So we don't really look at the entire spectrum.
No. See, in fact, I mean, one question that might come to the mind is, suppose you take an image and pass it through an encoder, right? So, if suppose there are, if I make M to be 100, so there are, let's say that there are 100 vectors. Now, are 100 vectors good enough to represent a space that is as versatile as ImageNet? Might be a question. Yes. Right? Actually, the way they do it is that they make the latent vector a two-dimensional grid, okay, where each of these columns, okay, are k-dimensional. So you have 1 to k. So what they do is they quantize each of these columns. So each column is quantized of the latent vector. You understood? So that's what they represent. So basically what they do is the latent space will be a two-dimensional thing. It's a k cross p dimensional latent space. Okay, where each of the p vectors in the latent space is quantized using the dictionary. You understood? So that way every image now will be represented using p vectors, okay, from the dictionary. That way it becomes versatile.
And are there any weights to each of these dictionary?
No. So decoder now will see a k cross p dimensional, grid. See, when I said that it is ZQ of xi, it is not one vector, right? It is the quantized version of this entire grid. That's what the decoder sees as an input. That's what they do in the VQA paper. Is this clear? So that's how it is not a single vector that is going as an input to the decoder. It is p number of vectors, right? Where all these p vectors come from this predefined dictionary. And how do you find which of the vector from the p dictionary that you should take is you pass the xi to the encoder, and encoder gives you a map, right? A grid of p vectors, and each of the columns of this p dimensional grid you quantize using the dictionary, and you give that as an input to the decoder.
But where is the variation coming from? I mean, randomness coming here, because if you have chosen a fixed set of k vectors, right? I mean, k size vectors, the output would always be the same, or?
No. During the training, of course, right? You take those p vectors and then you try to reconstruct it.
Correct. Okay.
Now the question is, how do you use this for generation, right?
Okay.
That is a question that I'll answer later.
Yeah, sure.
So right now, the way the template is define the architecture, right? And train it, and then you do the inference. I'm defining the architecture, and we have still not trained it. Let us train this, and then we'll do the inference. But it's a valid question. How do you generate from a VQVAE is a valid question. But did all of you understand what's happening, right, in terms of architecture and training? Any questions on that?
Sir, here for a given xi, we will receive only one vector ze of xi, right?
That is what I'm saying. So for images, what they do is, say this is a working offline error occurred. I don't know what error occurred. See, input will be let's say a 400 cross 600 image, okay? Okay. Output will be let's say 32 cross 50 dimensional vector, okay? Where 32 is your K and 50 is your P. What will be done is all of these i's, okay, will be in 32-dimensional space. What will be done is that each of these 32-dimensional vector, 50 vectors will be quantized using the dictionary. And the input of this will also be a 32 cross 50 dimensional grid. Do you see that? It's not one vector, it is a grid. And each vector in that grid is quantized using the dictionary. That's how they do it. Is this all right?
Sir, in the naive VAE, we used to get the mu and sigma vectors.
See, I told you, you look at this, right? I said that it's a latent space that is discrete and vector quantized and learnable. You should also say that the encoder is deterministic. It is not a probabilistic encoder.
No, sir, I'm talking about the dimension. So in the naive VAE, the mu e, we used to get one mu per dimension, right? Like for 600, 400 cross 600 image, we will be getting the mu vector of size 400 cross 600, right?
No, definitely not. See, I've been telling that multiple times, right? This is a k-dimensional thing. If you're
okay, like,
haven't you implemented VAE yet? See, this is a k-dimensional thing.
No, sir, I got confused here.
This is k-dimensional. This is also k-dimensional, assuming that it is a diagonal matrix. Told this multiple times. Got it?
Okay.
It is one mu with a k-dimensional thing, because see, this lies in a k-dimensional space, right? It is z. Z is in k, and therefore mu is also in k dimensions. Okay. Any other questions on the architecture of VQVAE? Okay, so now we will have to train this, right? Training VQVAE. Now the objective is again the elbow, right? It will have two parameters. It will have the encoder decoder parameters and also this lambda parameters. Note that lambda parameters are Z1 to Zm themselves, isn't it? Now the lambda parameters are Z1 to Zm themselves, right? Now the objective here is you simply do a reconstruction task. Okay? And there is this other thing which is reduce the KL divergence between the output of the, reduce the not the KL divergence, the norm between the output of the encoder and the quantized version of it. That's all. This is all the objective is. It's very, very simple. Right? This, you optimize this with respect to, so what is happening here is that the gradients xi, look at as ze of xi decoder. This will be zq of xi. This will be xi cap. So now you have here z1 through zm, right? Now, once to learn the encoder, of course, there is a forward pass like this, and there is a simple reverse pass, right? With the reconstruction term. Gradient with respect to phi. This is what you do. Okay. To learn the, of course, for the decoder also you do the same thing. To learn the latent space, what you should do is, you should take the gradients of latent dictionary. Okay. You have to take the gradient of this particular term with respect to z itself and then back propagate. See, z, you can take a, here we know how to take gradients with respect to parameters, right? We can also take gradients with respect to vectors themselves. And you see z1 to zm, okay? Actually, you have to take it with respect to all zi's here, zij's, where zj belongs to dictionary. Take the gradient with respect to the dictionary vectors themselves and then back propagate from the output, okay, till the till this space. So till the so you see this as another layer sort of, right, in the neural network. This is a dictionary. The gradients will flow from the output of the decoder till here. This is how it, and this is how you update the gradients. So now what will happen is your zj, you have to do it like vector by vector wise. Zj plus 1 will be zjt, randomly initialize that, minus some alpha times the gradient of the elbow, which is this term, with respect to z. Cj. This is all right. This is how you do it. This is how the latent vectors are learned. Any questions on this? Otherwise, it is simply an autoencoder training. You have the encoder decoder, you train both the encoder decoders through backpropagation. The one extra thing is you learn the latent dictionary vectors themselves by doing a backpropagation through the latent dictionaries. Is this all right? Any questions on this? This of you train a VQVAE. Go on.
Yeah, so I mean, can we see it like we are trying to find some basis vector of the data
There's no,
during the training?
it's not basis for data, no, it's you can say that it's the basis for the representation space of data.
Okay.
Data is being represented in the space. For that, you are trying to learn the basis.
And the number of vector that we choose would be a hyperparameter.
M is a hyperparameter.
Thanks.
Okay. Okay. So now this is how you train it. So now once you train this, you'll have to do inference. First thing that we'll do is the posterior inference or embedding extraction, right? This is what we call as embedding. Just straightforward, right? You have the encoder. Always for the posterior inference, you take the encoder. Its test goes as an input to the trained encoder. You will get a ZE X test. Okay. The embedding for X test is simply the vector quantized version of ZE. That's all. You have J equal to 1 through M. You search for the closest version in the quantized space. I've written as a star because we learned it already. This is the embedding. Is it all right? So as I said, typically what happens is, right, you take a grid of K cross P, right, and quantize each column. That is what is done. Now this embedding, right, is the state of the art that is used in all the text to image generative models. They take a VQVAE that is pre-trained on ImageNet. They take this embedding and use it for and train a diffusion model on top of these embeddings. Nobody starts, I mean, like the state of the art, right? People don't build diffusion models on data, or rather in the image space. They do it on the embeddings that are gotten by a VQVAE trained on ImageNet. Is this all right? Questions on this? How do you do posterior inference? Great.
Sir,
yeah.
What is P here? I mean, what should it be?
Hyperparameter. That's a hyperparameter that is typically used. I mean, if you look at the VQVAE paper, right? The first there is VQVAE 1 and VQVAE 2. I think in VQVAE 1 they take P to be lesser, and then they show that P should be. In fact, you can actually make it a 3-dimensional thing also, no? Where you make each of it a map. Depends. So that depends upon the kind of network hyperparameter choice that you make. Yeah.
Yes, sir. Thank you.
And you replace each of those columns by you vector quantize each of those columns. That's the point. Okay. 2, we have to do generation. See, VQVAEs are not typically used for generation. As I said, right, they are mostly used for embedding extraction, okay, or inference. But you can also do generation from it, generation or sampling from VQVAE. See, one thing that is to be noted is that because since the latent space is vector quantized, space is discrete, I'll write it as quantized. Quantized, okay. One does not know the distribution of it. You see that? One doesn't know the distribution of it. Right? See, in a VAE, we know that the latent space follows normal 0, 1. That's why post-training, we can take sample from normal 0, 1 and give it to the decoder, and we will get the output, right? Here, we don't know what the distribution of latent space is. So that's why what is done typically is that the way it is done is first extract embeddings of training data. You understood? So what is done is given x1 through xn from the training data, okay, get z1 through z, been using different notation for that, no? What shall we use? It's called the z cap 1 through z cap n, where z cap I is the embedding for xi, okay? You get this via encoders. So once by posterior inference, no, you get the embeddings. Then what is done is fit a GMM. Actually, what you can do is fit a generative model, train a generative model on top of these embeddings. This is the first step. This is the second step. You train a generative model on C1 cap through Zn cap. Now, this generative model can be a GMM, okay, or in the VQA paper, they train what is called as a pixel CNN, which is an autoregressive model. autoregressive generative model. We will see the autoregressive generative model later next in the course. So basically, you train a generative model on top of the latent embeddings that you got from the encoder. Okay, then now sample z cap new from the generative model on z1 cap to zn cap. Okay, then pass z cap new through the decoder to get cap new. Did you understand this? The problem is, unlike in a VAE, you don't know what the distribution of the latent space is, correct? Because it is discrete. Therefore, what is done is that once you learn the encoder decoder, you take all the training data and pass it through the encoder and get the corresponding embeddings. Now that becomes a new data set. Okay. On the embedding data set, you learn a generative model. Now you know how to sample from the latent space of the VQVAE, right? And therefore, what you can do is, once you learn a generative model on the latent space, then you sample from it and give it to the decoder, and decoder should give you a new data point. This is all right. In fact, people say that, I mean, there is also our experience that training a generative model on the latent space of a VQVAE is very difficult. And that's why VQVAE is typically not used as a generative model itself. What is done is PQVAE is used for posterior inference. You get the embeddings and use train a diffusion model on top of those embeddings, right? Yeah, in fact, this is what is done in a stable diffusion and all that. What they do is, actually, this is what is done. No, you train, it can be a GMM or it can be a pixel CNN or it can be a diffusion model. That's exactly what is done in stable diffusion. So basically, you take a VQVAE, get its embeddings, learn a generative model on the latent space, okay, and generate a new sample in the latent space of the VQVAE and give that new generated latent sample through the decoder and get the X new. That is exactly what is done in stable diffusion. And all this, imagine that you have Google's this thing, right? All the, I think it's JEN. It's that Google's engine, right? All of these commercially available things, that's exactly what they do. They take a VQVAE, train a generative model on the latent space of the VQVAE, and generate a new sample from the latent distribution of VQVAE and give it to the decoder to generate the image. And what you see is the image, but the generation is happening in the latent space. Okay, Sanchit?
Sir, if we are training a GMM on these embeddings Z1 to Z1 hat to Zn hat, so what shall be the mean and variances for a individual Gaussian model?
That is what is learned in a GMM. Yeah, in a GMM, you don't fix the mean and variance of the individual Gaussians. That's what you learn. You learn the mean and variance of individual components in a GMM. You're using EM.
Okay.
Okay. So yeah, forget about GMM right now, right? You can, I mean, as I said, no, in stable diffusion, etc. The model that is the generative model that is used on the latent space is actually a diffusion model, which we will see right now. Okay, so if you understood, good. So this is the end of VAEs in one form, because the diffusion models are also VAEs. But yeah, so in the naive form, this is the end of VAEs. See, I have not asked you to implement a VQVAE in your assignment because I thought it would be too much. But yeah, if any one of you have some bandwidth and time, I'd be happy to see you implementing
Have-
VQVAE. That would
You
be
have
nice
asked, sir.
if you can do that. Have I?
Yes, yes. You have asked VQV with discrete lattice space.
Then, so cruel of me. Then do it. Okay, I think then you should do it. Yeah, you should do it. Okay, so great. I thought I didn't expect this to take so much time, but it's worth it. It's fine. Okay, so shall we take a break? Been talking for 1.5 hours, 1 hour 45 minutes now. Yeah, as I said, I need to leave like 5 minutes to 11. So let's not take a long break. Let's take a short break, 10 minutes. 10:20 we'll be back. Is that okay?
Yes,
Or
sir.
do you need 15 minutes? 10 minutes is enough, I suppose. Yeah,
Sir,
let's
it's fine.
yeah. So please come back at 10:20 because we'll start diffusion models. Don't miss the introduction. That's very important. Yeah, let's reconvene in about 10 minutes. See you.
Sir, you are on mute if
Sir,
you are
you are
saying
on
something.
mute. Yeah, so you are on mute.
Oh my God, I got scared. Okay, I'm sorry. Yeah. So it's just speaking on mute. Okay. So the next topic that we will see in this course is about DDPMs, also called as expanded as denoising diffusion probabilistic models. I'm audible now, right?
Yes, sir, you're audible.
Okay. Okay. So now the state of the art generative models in all the vision language models that you see today, right, are based on DDPMs. They are neither VAEs or nor GANs, right? I mean, people have moved on onto these new class of models on called DDPMs, denoising diffusion probabilistic models. We'll study that. So basically, right, it's so DDPMs. So the plan is that I will set up the problem today in this class, okay, and then we will look at the rigorous math and all that in the next coming classes. There is one tutorial by you. What that is? It's a very nice tutorial. I'll put it on the chat now. Really very good. Okay, I encourage all of you to follow that and go through it. It will cover everything that I'll be doing in this class. Okay, I found it very. It's a 100-page tutorial. It's almost like a short book, but it is extremely good. Let me just put it here. You want me to put it on Teams also? That also I can do. Hold on. Teams. Oh, I think it's already there. How come? So whatever I put in here in the meeting chat, it will appear on the Teams, is it?
Yes,
Yes,
sir.
Yes, sir.
Okay, that's good. Tutorial on diffusion models. Please have a look at it. This is pretty much what I cover. Okay.
Sure, sir.
So it's a good tutorial. Have a look at it. Okay. So basically the idea is the following, right? DDPM is actually is a special case of VAE. Okay. Now you can actually see DDPM as a special case of VAE with the following properties. So if you look at this tutorial, right, he has actually derived the elbow, also done reparameterization, everything. Maybe I will just show you that once. Hold on. Do you see my screen?
Yes, sir.
You see, it's very recent. No, it has come out on 10th of September. It's pretty good. So they start with VAEs. Okay. So there is this encoder decoder definition of latent variable. And yeah, he also talks of GMM. See, this thing very much aligns with my narrative as well. I mean, you should trust me when I say that I did not build my narrative looking at this, because I've been teaching this course since 3 years. This man has used a very similar narrative as what I do. Okay, so then he goes to the evidence lower bound, constructing the evidence lower bound, and decomposition of the log likelihood as elbow, using the variational distribution, interpretation of elbow, right? Reconstruction and prior matching terms. Okay, so optimization in VAE, reparameterization, right? These are exactly the things that I did. I don't know, right? Maybe somebody who looked at my notes, but that was not public at all. I don't know how. But anyway, exactly the thing that I did. Okay, so VAE encoders and reparameterization tricks in high dimensions, scale divergence between two Gaussians, and this VAE training, and then they completed this concluding remark. Then they come to DDPMs. This is a very good tutorial. Okay, so please have a look at it. It will actually give you a lot of insights about VAE and also the DDPMs that I'll be covering. Okay, so, and also, as I said, right, thankfully it is very, very similar to the kind of story that I have told you, the narrative that I have built. So that very nicely aligns with what we have done. So please have a look at it. A minute. Charger is training. Let me bring my chargers now. A minute. Okay, so DDPM is actually a special case of VAE with the following properties. Okay, so we will see all those properties one by one. Hope you can hear me and see my screen, correct?
Yes, sir.
Yes, sir.
Okay. Okay. So one thing is that the first thing is that there are multiple latent spaces. Okay, unlike one latent space in a VAE. There are, yeah, so this is hierarchical. Hierarchical, okay. So there are multiple latent spaces here, unlike in a VAE where there is one latent space. So basically what happens in a VAE is that start from the data space, okay, project to the latent space, and from the latent space you get back to the data space, right? This is a VAE. Okay, in a DDPM diffusion model, what happens is start from X, get to the first latent space Z1, and from the first latent space you get to Z2, get to Z3, and some Zn, let's call it, right? And from Zn, get back to Zn minus 1, retrace it back. Do you understand this? Right? Instead of having one latent space, you have multiple latent spaces in a hierarchical fashion. Is it all right? So now why do we do that? Is that because, see, think of it like this. Start from data. Let's say that you have a very high dimensional data. Projecting, the motivation is that projecting it onto a latent space in one step and trying to compress it, making it compact in one step might be very difficult for the encoder, right? So typically projection from the data space to the latent space is the encoding process, and from the latent space back to the data space is the decoding process, right? Similarly, you have hierarchical encoding and you have a hierarchical decoding in a DDPM. Is this idea clear? So as I said, no, we will write rigorous math and we will concretize everything that we do eventually. But yeah, so high level, is this clear?
So can you comment on the dimension of G1, G2, G3,
We'll
Gn?
do that. We'll do that. We'll do that. One thing at a time. This is hierarchical thing. The second thing that you do is that the dimensionality of the latent space, of all the latent spaces, is same as that of the data space. So again, typically what happens in a VAE is that dimensionality of the latent space is much less compared to that of the data space, right? But in a DDPM, the dimensionality of the latent space is exactly same as that of the data space. Okay, that is the second property. The third property that is used is the encoding process is not learnable, but fixed with the Markov process. See, in a VAE, what do we do? So VAE, what we do is Q phi of Z given X, okay, is learned, right? Via elbow. Here, Q of Z given X is non-learnable, is fixed. So you see that phi is, there is no phi here. Do you understand? It is not learnable. The encoding process is defined using a Markov process. There is nothing to learn here. Is all right. So that implies that only the decoder is learned. There's no one decoding process is learned. So now if you incorporate all three of these properties, right, which is that you take hierarchical latent spaces and you match the dimensionality of the latent space to that of the data space, and you make the encoding process a fixed one but not learnable, then the resulting VAE is called DDPM. That's all it is. The rest is only algebra and mathematical details. So what we will do is we will incorporate these properties into a VAE and we will write down the elbow for this sort of a VAE. And when we optimize that and we do the algebra, we will end up having the loss functions for a DDPM. Okay, so that's why I taught GANs first and then came to VAEs, and then we are going to DDPM because DDPM is a special case of VAE with these properties. Any questions on this?
Sir, what does Markov process mean? Just a random process or?
Yeah, I'll tell you. See, for now, think of it like I'll write all the equations and it'll be clear, right? So basically, what do I mean by Markov process is that start from the data space, right? You go to the first latent space. From first latent space, you go to the second latent space. From the second latent space, you go to the third latent space, and so on, right? By Markov process, I mean that if you take the tth latent space, okay, it only depends on t minus first latent space, and it does not depend on anything else.
Okay, understood. Right? Time based.
There's no time per se here.
Iteration.
It's not even iteration, right? You can call it as the latent space index.
Understood. Yes.
I mean, you can call it time if you want. I mean, you can, if you want to see that as start from the data, you go the first time instant, you go to the first latent space, second time instant, you go to the second latent space, and so on. Okay. Any questions on this? On the high level formulation? Yeah, Sanchit.
Sir, so here are we saying that we are not taking the data batches, but one data point at a time?
See, you still do everything on a batch level. See,
Okay.
every analysis that we do is for one data point, right? Because doing it on a batch is only one other summation at the outside. Correct. All the VAE analysis, we did it for one data point. So now this is for one data point. Everything that I'm doing is for one data point. Okay.
Okay.
No, even sir, for VAE.
Like we are saying at time, like at one time we reached the first latent variable, and at the next time we reach the another latent variable. So that part, like, I was not clear.
There's no, I said there is no one time. See, in a VAE, I wrote it here, right? What do you do in a VAE? Start from the data point, get to the latent space using encoding, and get back to the data space. Now, in a DDPM, you start from one data point, go to the first latent space. From first latent space, you go to second latent space. From second latent space, go to third latent space, and so on. That's all. We are doing it for one data point. I mean, of course, everything that we do, we'll do it over batches. But yeah, but analysis we do for one data point, right? All the elbow, etc., we do it for one data point, assuming that we only have one data point, and you just put a summation outside later.
And sir, this encoding, is it probabilistic still?
It is probabilistic but fixed.
Probabilistic but fixed.
Not learnable. By fixed, I mean learnable. We'll write the equations, it will become more clear. Yeah. Okay, so let us get to the math now. Any other questions on this? Questions? Let's go on. Unfortunately, the community has used a different set of notations than VAE. So I will use the same notation as it is there in the papers and the other tutorials. So it's a weird notation. Please bear with me on that. So data is represented using X naught. Okay. So what used to be, I'll just write the things that we were doing earlier using some other color. This was our X. Okay. And latent space is represented using x1, x2 to xn. Now, x capital T. Please note that this is not the data points that we had. As I said, it is unfortunate because this is a very, very non-standard notation. Okay, so let's call this T. Latent space is typically represented using Z. Okay, But DDPM community, they represent that using X12, X capital T, and data is represented as X0. So this is what we used to call Z1, Z2 to ZT. Okay, so I'll write this not to be confused. With previous notations. Where X1 through Xn were data points. Okay, is that okay? Because see now from now to the end of DDPMs, we will be using this new notation. So now let me clarify. X0 is the data point. And also note that all that we are doing is for one data point. So we'll do it for a single data point. X1, X2 till Xt are latent vectors. Latent vectors corresponding to X0. Is this okay? So now the encoding process is that you start from X0, go to X1, and then from there to X2. This is the encoding process. This is latent vectors of same dimensions. Is this all right, notation wise? Yeah. Please get used to this notation because, as I said, no, very non-standard notation, but that's what the community uses. And I am not changing it. So just to ensure that notationally it is correct, consistent across. Don't know. No, this guy uses exactly the same terminology as I do. I'll show you this. That's a serendipity. Is my screen visible?
Yes, sir.
Look at this, no? X0, it is the original image, which is the same as X in VAE. Xt is the latent variable, which is same in Z in VAE. Okay. X1 and Xt minus 1, they are intermediate states or intermediate. They are also latent variables, but they are not white Gaussian. Yeah, that is okay. Yeah. So I strongly recommend all of you to go through this. Okay. So, I mean, of course, in parallel to what we have been doing, but yeah, so it's very consistent with what my narrative is and also the notations. Is the notation clear now? Please note that the dimensionality of all of these latent vectors are exactly same as that of the data space. I'll write that maybe. Time of X0, same of time of C for T in 1 through capital T. So note that X0 is your data vector. Is this clear? Is the notation clear? Okay. Now we will define the encoding process in DDPM. See, also I'll tell you why is it called the denoising diffusion probabilistic model. We'll not leave anything out, okay? So, but yeah, I'll give you the easiest narrative first and then I'll connect every dots, don't worry, okay? Let us define the encoding process in DDPM. So now what is encoding? That projection from X to Z is the encoding process, right? This is the encoding process. How is it done in DDPM? Is that it is done in a Markovian way. What does that mean? Means that you make your X1, which is the first latent variable, to be equal to alpha naught times X naught plus 1 minus alpha naught times epsilon, okay, where epsilon is coming from normal 0, 1. This is the definition of encoding in a DDPM. Okay. So now similarly, X2 is alpha 1 times X1 plus 1 minus alpha 1 times. So let's call this as epsilon 1 or epsilon naught, and this is as epsilon 1. So actually they are all samples from the same normal distribution. They are doing different samplings, that's all. X2 and so on. In general, you have X, the tth latent vector is given by alpha t times xt minus 1 plus 1 minus alpha t times some epsilon t, where epsilon t is coming from normal 0, 1. This is the encoding process. This is the fixed encoding process. You see that there is nothing learnable here. This is probabilistic, but there is nothing learnable. Is this clear?
Is it t minus 1, right? Alpha t minus 1, and as per the general X2 we kept as alpha 1 X1.
Yeah. I'll do that. I'll write that.
Is this still Markov process?
It is a Markov process. Just a second. I just want to be consistent with the notation. Just a second. I'm just looking at that P140. This is alpha t. Okay. People generally write this as alpha t. This is alpha 1. This is alpha 2. Again, it doesn't matter, but just want to be consistent. So where alpha 1 through alpha t, right, are fixed scalars. Between 0 and 1. Okay.
Epsilon index as well, sir.
Epsilon index. Epsilon index is okay. I mean, yeah. So see, epsilon, I can write it as epsilon every time. It's just sample from a normal distribution, right? There is nothing like sacrosanct about this 1, 2, etc. But okay, fine. You can call it epsilon t. So is this clear? Is this all right? Do you understand what's happening? See, what is happening is that you take the data point, okay? See, this can be seen as some noise, right? When you take some noise, scale it, add it to the data point. So that will give you the first latent vector. Okay. Then you take that first latent vector, okay, take some noise, scale it, add it, and then you get the second latent vector, and so on. So this is whatever I have written here, right? This is actually a first order Markov process with Gaussian transitions, because the noise that we are adding is Gaussian. What is the spelling of transition? No. TITION, is it? Or SION?
It's SITION.
SITION. Yeah. with Gaussian transitions. Okay. So basically what is happening is, right, you can see this as like this. Suppose we start with an image. Okay. So this is X naught. What are we doing? We are just taking some Gaussian noise with the same dimensions. Okay. Adding it to this. Of course, you scale it with alpha and add it with that. So you get so-called noisy version. This will give you the first latent space, right? And then you add another noise, and this is alpha 2, and you get image with more noise and so on, right? You keep doing it, and as a result, I would say that if you keep doing this at xt with sufficiently large t, this xt, right, xt will follow a normal distribution 0, 1. So this is called the stationary distribution of a Markov chain. Right? So if you create a Markov chain like this, it will go to a normal 0, 1 is what is known. Okay, so hold on, let me just show you a picture. This is how you create the encoding process. This is the encoding process of a Markov chain. Let me of a DDPM. Okay, let me just show you this. I mean, of course, your assignment will be one of your third assignment will be on this, so you will implement all this and appreciate it. Do you see my screen?
Yes, sir.
This is what I'm talking about. Starting from X naught, you create a sequence of latent variables by adding noise. Okay.
Sir, the picture is not zoomed in it.
Come
Can you
again?
go with that? That screen was not, it was not
Here
going to.
you see this here?
Yeah, now we can see.
This is the process, right? You start from X naught, just keep adding that noise and you get a encoding process. Is this all right?
Yes, sir.
Okay. Okay, so I think this is a good time to stop. So please again look at this and look at my notes. Huh? So we will continue from here from the next class. So we'll have to leave now. Okay, so the summary is that a DDPM is a VAE, a hierarchical VAE with multiple latent spaces, with the property that the dimensionality of the latent space is exactly equal to that of the data space. And the encoding is a fixed process. There's nothing learnable. What you do is you take the data and create a Markov chain by adding Gaussian noises, and that will give you the latent embeddings. So what do you do with it, and how does this become this thing, a generative model, and all that we'll see in the next class. So basically what we do is we will create a decoding model and we will write the elbow that we were writing for VAEs and then derive a loss function for it. That is what we'll do in the next class. Please have a read at that tutorial that I have shared, and also my handwritten notes is also there. There also I've done it, and yeah, and look at my notes and come prepared for the elbow and look at VAEs. Okay, the next class we will do the math for the diffusion models. That's all right. Again, thank you for being accommodative. Okay, so and sorry about moving everything 1 hour before. So you have a quiz now. Please wait. Let me just call Chandan. How can he not pick up? Chandan, I'm done with the class. Yeah, so can you please join that link? Students are here and then conduct the quiz. Huh? So I'll ask the students to wait, just join there and you can conduct the quiz. No, I just completed because I have to leave now. Yeah. So the thing is, see, one other thing, right? If after the quiz, if students have some time, if they can spare, you can maybe just take a tutorial or rather just do some, I mean, do that exam thing. I see. Okay, no problem. You can conduct the quiz and then leave. Okay. 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 So students are waiting. So you can please come online and. Okay. Thank you. Thank you. Yeah. Okay. So I just spoke with him. Chandan will be here in about 2-3 minutes, and please take that quiz, and then you can leave. We will meet next week.
Sir, the next quiz is supposed to be a week after the next one.
No. See, we have to do 6 quizzes, right? We will. I'll talk to Chandan. So we have this will be the 3rd quiz, right?
Yes, sir.
Will be 3rd quiz. We have 3 more. So we will. I and Chandan will discuss about it and let you know, because we have 4 more weeks and we need to do 3 quizzes, right? So what
Yes,
we
sir.
can do is we can skip on that Diwali week, and rest of the weeks we can have quiz every week.
Yes, sir.
We'll do it that way.
Sure. Yes, sir.
We'll do it that way. I will discuss about it and keep you notified on the WhatsApp group and Teams. Okay. Okay. I really have to leave now. So please take the quiz. I'll leave next week.
I'll take it.
Thank you, sir.
Okay. Thank you.
Thank you.
Bye.
Thank you.
All the best, sir, for your interview.
For my interview. Exactly. Thanks. Okay. See you. Bye.
Okay, sir. Bye.
Bye, sir.